Okay. Okay, so today I'm going to talk about quiet planting and the problem of refuting coloring, or colorings, or lower bounds on the chromatic number in random deregular graphs. And this is joint work with Jess at Berkeley, Tim and Alex in NYU, and Chris in Santa Fe. So the object that we're going to study, right, is a uniform deregular graph. Right, so this is just a uniform deregular random graph. And we're going to want to understand the computational hardness or efficiency of algorithms that handle colorings and cuts and things of this type. Right, so what is a coloring of the graph? What I mean by this is in the classical sense a coloring of the vertices. So a coloring of the vertices where no two vertices have the same color. Okay, so the way we formalize this is that we take some kind of assignment from the vertices of a graph to a set of k possible colors, so right, numbers 1 through k. And we say that, sigma is a coloring for G, for a graph G, if for every edge in G, we have that sigma I is different than sigma J. Right? There is no two vertices that are connected that have the same color. Okay, and so now, with this definition, we can easily define the chromatic number. Right? So the chromatic number for a graph G is just the smallest possible such k. Right, so of course if I have more colors, the graph is easier to color, so I take the smallest possible one that I can do. And now we can ask many questions about the chromatic number, right? What are good algorithms to compute it? What are good algorithms to find coloring? What does it typically look like on a deregular random graph? How do algorithms behave on a deregular graph, and so on and so forth? And so we know a lot of this, much of this is classical, and we know that if G is drawn from the deregular graphs, then the typical coloring number for G is something like, make sure I get this right, D over 2 log D. Okay, so this means that if I draw a uniform random deregular graph, then typically I'm going to get a graph whose chromatic number is D over 2 log D. Right, and everywhere in all this talk, there's two limits, right? I fix D and I push n to infinity, and then I sort of mean things for large D, right? But when D is considered fixed and n goes to infinity, but then D is considered large, so there's sort of this double limit. Okay, that's very classical in this thing. Right, so we know that computing chromatic numbers is NP hard in the worst case, but now there's a question that has been around for many years. Of can we actually, given a uniform deregular graph, can we, with high probability, find a coloring with around this many colors? Right, and so this is not known, and in fact, it's not so hard to be able to color the graph with double the colors, and so far we don't have any significant improvement over that. So this is the chromatic number of the typical chromatic number of the deregular graph. But if you actually want to efficiently find the coloring, then we need roughly double the number of colors, and this is essentially unimprovable. Right? So this is the type of questions that one can ask when we talk about trying to figure out efficient algorithms in sort of the average case of problems. Okay? And so what I'm going to talk about today is a little different. What I'm interested in is in refuting the existence of colorings. Okay, so let me explain what I mean by this. The players in the game are exactly the same. The objects are all the same. Maybe I'll leave this up. Okay, so I can say efficiently, maybe I should write this, efficiently one can find coloring with roughly twice that. So finding a coloring is an upper bound on the chromatic number. Now I can ask, what upper bounds can we find? Right? So the question I'm interested in here is, for which values of k can we refute the existence of k coloring on a random irregular graph with high probability. Okay, so what do I mean by this is, of course, I want to give a lower bound on the chromatic number. Right? I want to say, well, I'm sure for this graph you cannot do it with less than a certain amount of colors. Right? Of course, if I give just a lower bound of this minus a little bit, then of course this is a lower bound with high probability. Right? So this could be a lower bound that I can produce. I just say this minus epsilon, or maybe times 1 minus epsilon, or something like this. But here what I want is I want the lower bound to be a proof. Right? So the lower bound needs to hold pointwise for every graph. Right? So it needs to be a proof. Right? It needs to be a proof of non-colorability. Okay? So given a graph, I need to be able to prove that it does not have a coloring with k colors. And now I want to ask, for a deregular graph, what's the typical value of k for which I can do this? Okay, if there's any questions, please, please go ahead and ask. Okay, so now the natural way to attack this problem, to try to understand what we can say about this, is actually to formulate things in terms of trying to refute large cuts in the graph, right? Because a coloring, in a way, is just a very, very large cut. Right, so I can define, if instead of wanting, right, I say that an edge gets cut by the coloring, by the assignment, if it differs on two sides of the edge, the assignment, now instead of cutting every single edge, I can just ask to cut as much as possible, right? And this will be sort of the most natural way to address this problem. Okay, so I'm going to talk about the maximum k cut. Right, and this I'm just going to say for a graph G, this is the maximum of all assignments. The number of, so I normalize this, so I take the number of edges, right? The number of edges such that the edge gets cut. Right? If I think of I can think now of the colors as communities, and then it's very clear that I'm just cutting edges, divided by the total number of edges. Right, so now I can define this, and coloring is nothing more. This is counting the number of bichromatic edges. So coloring is nothing more but simply asking the question of, for which case can I make sure that this is not 1? So the coloring, right, the chromatic number is nothing else but the minimum k for which mck of G is equal to 1. Right? And so this means that upper bounds on mck give me lower bounds on coloring. Right? So really, in order to be able to refute the existence of colorings, it suffices, or what I should focus on is trying to find upper bounds of MCK, right? So the goal will be to give computational, right? So efficient, maybe use the word efficient. Efficient upper bounds of MCK. Okay. Okay, so a classical one, of course, is to take a spectral upper bound. Right? This is sort of the most classical. Okay, the classical is simply a spectral upper bound. Right, so I will not derive it here, but this goes back to the 70s, to the work of Hoffman. Right, this is sometimes known as Hoffman bound, but it would take me 10 minutes to derive. So Hoffman's bound from the 70s. Okay, and so Hoffman bound says that the maximum k cut of a graph is smaller or equal than k minus 1 over k times, where, remember, this is normalized, right? It's the fraction of edges that get cut. 1 plus, where this is the adjacency matrix of the graph over t. Okay, so I'm writing this with this weird thing of putting the plus and the minus, but this is for a reason. One is that the minimum eigenvalue of the adjacency matrix is, of course, negative. Right? It's very easy to see this because the trace of the adjacency matrix is 0. Right? And so if I don't have this term, then if I just have k minus 1 over k times 1, this is exactly what a randomly picked k cut will cut. Right? If I just pick a random assignment, this will be the average size of the cut, and so I can view this as sort of the deviation from that average. But now we have an algorithm that bounds the k cut, which is given a graph, we compute is the minimum eigenvalue of the adjacency matrix. This is something we can do efficiently. And then from that, we get an upper bound on the maximum k cut. And we can ask ourselves, well, if this upper bound is smaller than 1, then it means the graph cannot be colored with k colors. Right? This is known as the Hoffman bound for coloring. Okay. So now, of course, what we need to ask ourselves is, for a deregular graph, how good is this upper bound? Right, so for a deregular graph, so for a graph drawn by the, as a uniform deregular graph on n nodes, then there's a theorem of Friedman that tells us essentially what is the typical value of the minimum eigenvalue of A, which then we can plug in and we see what the upper bound usually looks like. Right, so this is from 2003, and it says the minimum eigenvalue of A, the adjacency matrix of a graph drawn from the uniform distribution over deregular graphs, is minus 2 square root minus 1 plus. Okay, so this means that typically, right, the Hoffman bound, right, or so the spectral bound, for uniform deregular graphs, it gives, right, I just have to replace it. 1 plus. So we can refute the existence in a typical deregular graph drawn from the uniform distribution. We can refute the existence of a k cut bigger than this. And now we just have to work out what is the value of k for which this is 1, right? So now we just have to write this equals to 1 and see what k we get. And the k that you get is k is roughly something like square root d over 2. So this means that the Hoffman bound tells us that you cannot color a graph with less colors than square root d over 2. Okay, so let me erase this part. Okay, so this means that the spectral bound, or the Hoffman bound, right, refutes colorings with k something like square root d over 2. Right? I'm not worrying too much about lower order terms. Okay, so it gives a we call an efficient lower bound. Lower bound, yes, of square root d over 2. So now the question is this improvable? Right? Can we do any better than this? Right? And in particular, we know that the true, right, if we think of what the true value, the right value for the chromatic number of a G and D, right, was something like D over 2 log D. Right? And here the best lower bound we can do is much, much smaller. Right? We're talking about square root D over 2. Right? Best. Or spectral. Right? This is similar to the other problem of finding colors with the least amount of colors, on which the most, in order to find efficiently a coloring, we need colors that's somewhere over here. Right? But the problem here is different. It's about refuting. Okay, if anything is not clear, please ask. Okay, so the big question is, can we improve over this? And we know that, so a natural thing to try would be something like the Lova's theta function, right? Sort of a sum of squares lower bound for this. And we know that the Lova's theta function doesn't, this is known in the literature that the Lova's theta function doesn't improve over this. And what I'm going to do in this talk is I'm going to give evidence that indeed this is the right threshold. Right? So the goal of this talk, we give evidence that this is not improvable. Okay, so this is the goal for today. I'll explain to you what kind of evidence and how we build such evidence. Okay, let me erase everything. Okay, and so it gives evidence that the spectral bound is actually optimal. So how do we give such evidence? How do we argue that something cannot be refuted? Right. So the way we do it is via what we call a quiet planting. Right. This name has already been used in the literature. Okay. So the idea is to generate a distribution of d-regular graphs, for which the thing that we're trying to refute is actually true, but for which we believe that distinguishing it between a uniformly drawn d-regular graph is computationally hard. Because if you can build such a family, such a distribution, then this means that if you had an algorithm to refute this problem on a uniformly drawn d-regular graph, you could use this algorithm as a test to distinguish between the two distributions. And we believe that this kind of distinguishing efficiently is not possible. Right? So this is the strategy. Okay, so what would be the trivial option? The trivial option would be to do essentially the stochastic block model, right? So we would say, we would pick sigma, we would fix sigma in assignment, and pick eta. Eta is going to be the strength of the planting, right? The size of the cut. Now, because of not to clash too much with the literature and community detection, because usually in the stochastic block model we plant more edges within communities and not across communities like we're doing here, all our parameters are going to be negative, so that they look just like the ones in the literature on the stochastic block model. Right? But eta, the more negative it is, the more structure we're planting, and 0 is planting nothing. Right, and now we draw the regular graph uniformly at random, conditioned on, so condition right, the number of edges cut times sigma divided by the total number of edges is equal to k minus 1 over k, 1 minus theta. Right? And so here you can see, right, the edge gets bigger the more negative eta is, and if eta is 0, it's just looking like a completely random cut. Right? And the way we should think about this is that, we have, I'll use another color, right, eta takes values between 0 and minus 1 over k minus 1. Right? And this corresponds to absolutely no planting. And this corresponds to planting a colony. Okay. All right, this is the value in which the cut gets exactly 1, and here it's the value in which the cut looks completely random. Okay. And so this model is oftentimes, we call it, this is oftentimes called just a stochastic block model for deregular graphs. All right, so I'll call it ND K. And so now, the point is that there is evidence, and I'll talk a little bit about this evidence. I mean, many of you know what I'm talking about. But there is evidence that G and D versus G SBM and D K theta, distinguishing between these two distributions, meaning you get a sample from one and a sample from the other, and in polynomial time you have to tell where it came from, is hard below the so-called Kasten-Stiegen. It's hard if D is smaller than, I'll call here Kasten-Stiegen threshold, it's a function of eta, which is equal to 1 over eta squared plus 1. Okay, and we'll call this the SPM conjecture. Okay, the point is that the SPM conjecture now, right, if these are hard to distinguish and this one has a big cut, then we could have never refuted the fact that this might have a big cut also, right? That's the way in which this is used. Right, so the SPM conjecture will imply that it is inefficient to not possible to efficiently refute or upper bound better than Okay, so if you believe the SPM conjecture, because this is the size at the Kasten-Stiegen threshold exactly until when they're still hard to distinguish, this is the size of the cut we're planting in the stochastic block model, then it means that we couldn't have refuted the existence of it in the sort of white noise graph of just uniform deregular graph. Right, but you might notice, now I don't have it in the board, that there's a factor of 2 missing. right? The Friedman, you may remember the Friedman eigenvalue is a factor of 2, and the factor of 2 is not there. Right, so this is being suboptimal by a factor of 2. And in fact, you can work it out. I'll save you the calculations. But for coloring, this gives k roughly square root of d. And so it argues that it is impossible to, it is computationally hard to do a lower bound better than square root of d. Okay, so not possible to efficiently refute better than this. Okay, but this has a gap. It's already in the right order, but there's an important gap here that the spectral bound was able to refute it at square root d over 2, and now we argue that nothing can be done better than square root d if you believe the SVM conjecture, but there's still a gap between half square root d and square root d that we don't know if it's possible to refute or not. Right? So this is different. Not. Okay, so it could be that somewhere there could be an improvement to the spectral bound of a factor of 2, essentially, potentially, or this does not rule out the existence of such a thing. Okay. So what we do, and what I'll do in the rest of this talk, is explain how to do a better planting that gets all the way to square root d over 2. Right? And so in order to sort of try to come up with a better planting, we need to understand what's wrong with this one. Right? What's happening here that we're planting a cut of a certain size, but somehow it's being visible a little too soon. And what's happening is sort of the same thing as this BBP push-out phenomena that happens in spiked matrix models. In say spiked Wigner models and so on, in which if we plant a rank 1 perturbation on a matrix, even if it's not quite at the edge of the spectrum of a random matrix, will push out an eigenvector further. Right? This is what's referred as the push-out phenomena in random matrices. And it turns out that this is exactly what's happening here, and once we detect that, it's fixable. Another maybe way of thinking about this is that maybe this is not the right conditioning, right? Maybe we shouldn't be picking an assignment and then conditioning. Maybe we should be conditioning on the existence of an assignment, but it's not quite so clear how to do that. And that is not how we fix this. Okay? So in order to explain how I fix this, then let me first describe the problem, the issue on a simpler example where it's easier to see. So the issue is some type of BBP push-out phenomenon. Okay, so if you know what this is, then maybe you'll see why this is the issue. If you don't know, it's okay. I'll give an example that I think hopefully will clarify. And the example that I'm going to give, I mean, I won't justify why, but essentially exactly corresponds to the problem in the graphs when k is equal to 2, when we're just trying to split into communities. Right? That's the example has a lot of precise connections with the case of trying to upper bound cuts of just in 2 clusters, graphs in 2 clusters. Okay, so let's say we have a Wigner matrix, so an n by n matrix whose entry is symmetric, whose entries are IID Gaussians, except for the fact that they have to be symmetric. And now I ask the question that I want to upper bound the quadratic form of in the hypercube on it. Right? So I want to understand the maximum okay, so I'm going to normalize this so that there's no factors of n. So I'm going to take 3 halves here. Right, and you can already see how this seems to be related to the max cut problem, right? If this is the adjacency, plus or minus 1 is sort of which of the clusters you put in, and it's counting edges, you have to massage it a little, but that's exactly what it is. It has very precise connections to it, and one-to-one correspondences. So if I want to understand the value of this, and say I want to upper bound it, then it turns out that the value of this is typically twice the so-called Parisi number. This is like 1.5. Okay. But now if I want to upper bound it, the most natural way to upper bound it is to say, instead of maximizing the hypercube, I'm going to just maximize on the sphere. Right? So in particular, this is smaller or equal than the maximizing value of W. Right, times n, because that's the L2 norm square of this point, but there was an n to the 3 halves, so I have to divide by n to the 1 half. Right? And this is basically Hoffman's bound in this language. Right? And the value of this we understand very well. The value of this is 2. Okay. So now we have the same kind of issue where the right value for this optimization problem here is not finding a best cut, it's finding maximizing some quadratic form, is 1.5, but our upper bound, efficient upper bound is 2. And now if we try to plant a solution, and we do exactly the same thing we did before, in which we pick an assignment x, right? And we try to condition, we pick x in plus or minus 1 to the n, and we try to, right? And we try to condition on this. Essentially, the object we're going to be building is W prime, which is lambda. I'm going to normalize this way, xx transpose over n, right? Because this is the L2, this is now the norm of this, so I'm just making it all be norm 1. Okay, and I'll divide here wherever n. Okay, don't worry too much about the factors of n, it's just so that everything works out. Okay, and now basically, if I want to make sure, right, if I want to condition on x having the quadratic form 2, then basically I should take lambda to be something like 2 in this construction. Right, now it might not be clear why this is the conditioning, but if you think about it, because they're Gaussians, the condition is essentially this. It would just be this, and you would need that x transpose wx is 0, but it'll be almost 0, so this won't really make much of a difference. Right, but the problem is if I do this, if I put this eigenvalue, this eigenvector x, right, if I plant it at lambda equals 2, actually, the maximum eigenvalue of W prime is going to be roughly 2.5. So when we pick a lambda that's bigger than 1, we know that the value that we see here will always be lambda plus 1 over lambda. In particular, you get 2.5. Right, so what's happening, if you look at the spectrum of this matrix, this is understood from the work of Wein, Benarus, and Béchier and others, that essentially, even though if you look at the semicircular law, the spectrum of the matrix, even though you're planting something inside, right, even though what you're adding, the strength of it is something inside, because it still has correlations with the noise, you will create an eigenvalue outside. We'll have this so-called push-out phenomenon. Right, and in a way, this is good news if you're trying to do high-dimensional statistics and PCA and so on, but now for our case is bad news, right? Because we're trying to prove loyalty. And so what's one way to fix this? So what we can do, and what we did to argue that indeed this upper bound was an improvable, so this was joint work with his student. Okay, so this and Alex Wein from NYU, we basically showed that, or argued that this was an improvable, and what we did was we built another kind of quiet planting, in which essentially what we do is we grab the matrix and we rotate its spectrum so that the vector x that we want to have quadratic form close to 2 shows up on the top of the spectrum. So instead of doing some additive like this, we actually grab the matrix and we do sort of a spectral planting. We call this a spectral planting. Now the problem is that this is actually, this is not easy to do in the graphs, right? Because for Wigner matrices, since the eigenvectors are completely hard distributed and so on, we can split the eigenvalues from the eigenvectors and we can sort of do whatever we want with them. But on graphs, if you get the adjacency of the graph and try to rotate its eigenspaces, you're not going to get a graph, right? So one needs to be careful how to plant. Okay, but this is and so one way to plant, which might seem like a cheap trick, is if you plant it to be exactly an eigenvector. So one planting that we could have done here is to draw W, sort of the noise part, if you will, not only to be orthogonal to X in the sense of X transpose WX being 0, but actually so that all eigenvectors of W are orthogonal to X. Because then there is no collision between the signal and the noise, and the push-out phenomena can happen. Right, so I guess the message here is if we plant the real eigenvector, there is no push-out. Now you might say, okay, if you plant exactly an eigenvector, then this isn't really quiet. Because you just take the spectral decomposition and I go see if there's any vector there that looks suspicious. Right, so that's true, and this is a little like the problems with XOR set and so on. So what we do is we make a planting of this type, and then we do some kind of noise operator just to shake the problem a little so that it's no longer an eigenvector. Right, so you actually plant something that is not hard to find, just happens to be hard to find for things like belief propagation, or semi-definite programming hierarchies, or low-degree method, or things of this type. And then you shake it a little with some kind of noise operator that would not affect the performance of those algorithms, and you sort of hope that it will destroy any algorithm that uses this extra algebraic structure. Right? So this is the strategy. Okay, so let me tell you what the planting is. Okay, so the idea is to plant with a more structured model in which the thing we plant is an eigenvector of the problem, and this is the so-called equitable block model. Right, in some parts of the literature it's called the regular SVM, okay? And so we call it equitable SVM, and so I'll write it G and D. K, eta, same thing, equitable. And the strategy will be, again, you pick, right? Instead of sort of structuring it less so that it's more quiet, we actually structure it more. Right? The same way that if we forced it to be an eigenvector, the issue with the push out goes away. I pick that and choose the eta, negative. Right? And now take the model on which, the cut, so I'll write here, the cut on sigma of G is what you want it to be. Okay, -1 of K minus eta. But right, so this is what we did for just the normal stochastic block model, is to draw it conditional on this, but now it's more structured. And the point is that all the neighborhoods of all the graphs are going to look the same. Right? So each node, the extra structure is that each node will connect to exactly d eta plus 1 minus eta k in the same community. And d 1 minus eta over k in the other each of the other communities. Each of Okay, so this model is much more structured because each node has a prescribed number of neighbors in its own community and a prescribed number of neighbors in all of its other communities. Right, and in fact, if you think about it, it's not so hard to see that this will make the sigma be an eigenvector of the adjacency matrix. Right, and so now the equitable stochastic block model conjecture, right, says that this is more quiet, that really a noisy version right, so you draw the graph and then you rewire some edges at random. The G and D versus G and D K eta equitable is hard to distinguish if D over if D is smaller than the Castanstigan threshold for this equitable model, which is equal to okay, so I have to tell you a few things. What does this mean for our problem, and why do we believe this conjecture? So let me tell you first what this means for our problem. So this means, or this would imply, right, that MCK, an upper bound better than essentially the spectral upper bound, right? Is that improvable? Right, and for coloring, this gives exactly the value of, like, the graph, the equitable model is exactly the square root d over 2. Right, which was the Hoffman bound anyway. So the message is, right, so the equitable stochastic block model conjecture, right, implies that Hoffman's bound is unimprovable. Okay. Is unimprovable, and in the sense that there is no efficient algorithm that does better than the spectral bound, right? Because the planting is done all the way until the Hoffman bound is tight. And indeed, and more, before I erase, let me tell you a little more. For k equals 2, in the particular case of k equals 2, right, this gives a proposal for a quiet planting of a max cut on a deregular graph on G and GMD on a random deregular graph, a typical random graph, matching the spectral threshold. Right, there's been some recent work trying to show that the spectral, arguing that the spectral threshold, the spectral bound was optimal in this case by proving that sum of squares cannot improve it, sum of squares degree 4 cannot improve it, and so on. But the method that, in a way, for the Gaussian analog of this, we had also a result saying that the sum of squares 4 doesn't improve over the spectral bound there, which corresponds to the spectral bound. But nowhere in our construction would we have a guess of what a planting might look like, of what a graph that from the viewpoint of a computationally efficient observer looks just like a random deregular graph, but whose cut is actually of that size. Okay? So now, in my last 5 minutes, do I have 5 minutes? Yeah? Good. So in my last 5 minutes, let me just tell you about what is the evidence that we have for this conjecture, and some of the issues that it has, and where it needs some work. Right, so the nature of the evidence for this conjecture is very much like the evidence for the normal stochastic walk model conjecture. So we have three sort of independent pieces of evidence, one of which is the normal Kestenstieg and BP analysis. Right, so we analyze when is it that we believe propagation could find this planted assignment. By understanding when is it that that BP is stable all around an informative fixed point. Then we have evidence based on local statistics STP hierarchy. Okay. I won't say much about this hierarchy, but you can think of it as a type of sum of squares hierarchy, but that is more designed for distinguishing two distributions rather than refuting the existence of some object or proving a certain inequality. Right? Usually the way we think of the STP, if say we want to find the best partition or the planted partition in the stochastic block model, we think of trying to minimize the minimum bisection, and we might say that, yeah, it did not come from the stochastic block model if this is too high, say, for example. Right? But when we're trying to distinguish two distributions, it's not clear that, we came up with a statistic of a minimum bisection for distinguishing in the stochastic block model two communities. Is a very natural one, but one might come up with a different statistic, some kind of statistic on the graph that may be better. And so the local statistics sort of STP hierarchy sort of searches among such statistics and tries to distinguish the two distributions. And you can read more about it in our paper. There's references to the original papers of Jess and others that describe this. Okay. And the other kind of evidence is of low degree, using the so-called low degree method on a Gaussian analog. So I won't say much about this, but very much like that Gaussian problem that I described corresponds to the k=2 problem on the graph. You can come up with sort of a multi-spike or high-rank spike model that will correspond to this problem in a certain way, and then once the translation is done, this method of this low-degree method can show hardness in that Gaussian model. Okay. So this is the kind of evidence. Okay, so what are issues that what are things that need some thought, at least, and probably a bit of work. One is, what should a noise operator look like? I mean, in general, we probably should understand a bit more this issue where these methods, the prediction that these methods make on problems that might have a very brittle algebraic structure, such as XOR SAT and so on, we believe that they are the right prediction of hardness once you shake the problem a little and you add a bit of noise or you push it through some kind of noise operator. Okay, so we suspect the same thing to be true here, but it's not completely obvious because, in particular, if we want to plant an actual coloring, then the noise operator better not add edges within a color. And so the noise operator needs to know sigma in order to act on the graph, and it's not quite clear that this is okay. I mean, it feels fine, but it's hard to argue that this is okay. And if you argue that this is okay, it's unclear where to stop. Right? And so if you're not okay with the noise operator depending on sigma, then what we can really argue is not about colorings, but sort of near colorings. Okay? Then there's another very interesting issue, which is with integrality. So there are integrality issues, not integrality in the sense of integrality gaps on STP, but in the sense of numbers having to be integers. Okay, and the problem is that each node needs to be connected, right? Remember, to d eta plus 1 minus eta k to the same community, and to d 1 minus eta k nodes on the other community. So these numbers better be integers. Right? If these numbers are not integers, then I cannot build my graph, right? Because they need to be exactly this number and exactly this number. And so they have integrality conditions, and integrality conditions essentially read that k needs to divide 1 minus eta d. Right? So this needs to be an integer and needs to be an integer multiple of k. And so it turns out, I mean, for the sake of, in the interest of time, I won't derive this, but it turns out that if d is much bigger than k squared, then this is not a problem. Then the effect of these integrality conditions is neglectable. Okay? For coloring, there's a special thing going on where the integrality conditions are a little less strong, because since you have 0 connections to your own community, one of these numbers is 0 and it's already an integer by default. And so for coloring is also not an issue. Right? So in these cases, it's not really a problem. Now, for very small d, very weird things might happen. Right? So for very small d, it might be a problem. Right? And so in particular, for very small d, we don't quite know what to do. I mean, there's of course, if the d is just right, so that the integer conditions are satisfied, then everything is fine, and the results become very non-asymptotic. But for very small d on which this is not the case, then yeah, this is tough. And sort of a very, particularly bad example is to take d equals 3 and k equals 2. Okay, so I'm trying to find the max cut on a 3 regular graph. So it turns out that the spectral bound, okay, so the spectral bound bounds something like 0.97. Okay? So it's just shy of being completely meaningless. Okay? It says that the biggest cut you can put on a 3 regular graph, the certificate that you can make is that it cannot be bigger than 0.97. If you work out what Hoffman and then Friedman's result give you, it gives you 0.97. But if you think about it, it says that most edges need to go to the other community. Very few edges go to the within community. But if you have only 3 edges to launch, and everyone needs to launch exactly the same number to every cluster, then you have to send one to the same community, and you have to send the other 2 to the other community. Right? There's no other option, because you cannot send all 3 to the other community, otherwise you'd be 1. So this means that the planting, in this case, which is sort of particularly bad, pretty sure just the worst possible one, then actually the planting that we make only plants 2/3, only plants a cut of 2/3, which even more unfortunately, it's actually smaller than the largest cut that the graph already had by itself. Right? So as d grows, none of this will happen. But for fixed d, the construction can be quite bad because of the integral conditions. And there's a very interesting question of what can we do for small d? And we have some ideas of how to potentially adapt the question. Because at the end of the day, it almost feels like a question in spectral graph theory, but it's not quite clear how to do this. Okay, thank you all for your attention.